All right, party people, we're back for round 2. This is test review number 2 for the graph theory test. Describe how you can determine if a graph is an Euler path or an Euler circuit. So a path has 2 odd vertices. A circuit has all even vertices. If something does not fall under those 2 categories, then it is neither of the things. So a path has exactly 2 odd vertices. A circuit has all even vertices. So what we're talking about with evens and odds, A, you focus on A, you count how many edges are coming off of A. A has a degree of 2. B has a degree of 3. 1, 2, 3. C has a degree of 2. D has a degree of 5. E has a degree of 4. F has a degree of 2. G has a degree of 4. And H has a degree of 4. So when we ask about what type of graph we are looking at, we are looking at a path. So if we have a path and you want to write the sequence for the graph, rule of thumb for a path is that you want to start at an odd and you want to end at the other odd. So for example, I would want to start at B and I will end at D. If I can make that happen, I'll be able to hit a path every single thing. Now, I may make a mistake. We'll see. Let's see what happens here. So let's just say I start at B and I go up to A, down to D. All right. So if I want to go maybe now C, B, I would come back to D. I'm not done. I clearly haven't done the other side yet. So let's go E, F, G, H, back to G, back to E, down to H, and back to D. That would be my path. Again, I started at an odd and I ended at the other odd. I did go through B and D multiple times, but pathway-wise and vertex-wise, I ended and started at an odd. All right, determining if we have a path, a circuit, or neither has everything to do with your degrees. So this is a 2, this is a 4, 3, 2, 3, 4. I would call that a pathway. Exactly 2 odds. All right, 4, 2, 4, 4, 4, and 2. That is a circuit, all evens. All right, so 2, 2, 3, 4, 2, 2, 3, 3, 3. That is neither of the things because it has more than 2 odds, or even just 1 odd. If it was exactly 1 odd, it would also be a neither. All right, the minimum number of hours it would take for a snowplow operator to plow all the roads of this town have to return to the same place. So the idea here, the minimum number of hours you have to return to the same starting place, I need to identify my odd vertices. All right, my odd vertices are D and let me see, C, G, B, D and B. Now, the game plan is between D and B, I want the most efficient path or route from D to B. So if I go, let's see, D to C to B, that is 18. Let's see, if I go D, try again, D to F to G to B. So D, F, G, B is 15. That's more efficient already. Let's try it again. What if I go, let's see, I could go D to F to C to B. DFCB is 16. That is not most efficient. Let's see, I could do D to C to G to B. DCGB, that's going to be 20. That's definitely not it. Okay, so my most efficient route is DFGB. So I'm going to create a copy of those edges. So I literally am going to add in another 5, and then another 5, and then another 5. At this point, we now have a circuit, and we would trace the circuit. So if we want to trace this circuit, everything's even at this point, so we can start wherever we want to. Let's see. So maybe we'll go AB to C to D to E to F. And I'm going to come back up to D, back down to F, go up to C, come down to G, come back to F and back to G, go up to B, down to G, and back to A. And if I wanted that, I would add up every number, including the new ones that I currently have. So 6 plus 9 plus 9 plus 2 plus 7 plus 5 plus 5 plus 2 plus 5 plus 5 plus 11 plus 5 plus 5 plus 7. And we would get that total. So let's see what we got for a total. 17, 28, 38, 40, 57, 59, 68, 74, 83 would be the minimum amount of time needed to make it as efficient as possible. Minimal spanning tree. Now, minimal spanning tree is slightly different. Minimal spanning tree is the idea that I want to cover every vertex, but don't particularly need every single edge. So one of my recommendations, if it won't already be drawn for you on the test, it may be, is you just create a different version of your vertices that you already have and start connecting with the smallest number you can find. So A to D is a 2. I see another 2 from E to H. Sweet, I see a 3 down the middle here. Let's see, next number would be a 4. And then we have another 4 up here. Okay, let's see, a 5. Well, I've got 2 locations for 5s. I don't need both of them. Let's say I'm going to use this 5. If I use this 5, I don't need the other 5 because it would create a cycle. It would over-connect. Now, I do need to connect to F, either from B or from H, and the shortest one from H is from H, so we're going to get a 6. I don't need the DH diagonal, the 7, and that is what I would call my minimal spanning tree. Again, just start with your smallest numbers, connect. If you create a cycle at any point in time, you've done too much. And just use the smallest numbers that you can come across with to get every point connected to something else. And again, if I wanted to add all this up, I would literally just add all this up. Let's see what we've got. 4, 5 is 9, 11, 15, 18, 20, 26 would be my minimal spanning tree. Last question on here, we're going to make a graph of things that we do not pair together. Now we're going to draw lines between things you would not pair, because if it's connected, we don't want to put it together, so we know what we're serving. So if you read this, let's see, 1, 2, 3, 4, 5, 6, 7. I need 7 vertices. So C, B, K, S, P, Z, M. All right, C would pair with B and M. Now I know we don't want to put those together, but when I color, I can't make the things connected the same color. Therefore, not together is what we want to connect. All right, B does not connect with C or S. K does not connect with M. See, S does not connect with B and P. P does not connect with S. Z does not connect with C and M. And M does not connect with C, with K and Z. There would be my graph. And to answer the list of dishes that you could serve to your friends, I need to start coloring. So let's say I color C1. B cannot be 1, but C and K could be 1. It's not connected to C. So K is a 1. C and S are a 1, and S is not connected to K. Let's see. P and C aren't together, but P is with S, so I can't use that. I can't use Z and M. All right, so these can be served together. If B is 2, B can go with P. That's correct. B can go with Z. All these 2's are not connected. B can't go with, or sorry, could go with M, but M can't go with Z. So M can't go with something we already have a 2. So then I would call this a 3. So it looks like together would be C, K, S, B, P, and Z, and then M. So together, together, and together. There we go. Hopefully that makes some sense. Good luck studying. I'm sure you guys are going to do great on this test.